Favorite bubbles is the dancing bubble. Let me show you here. So this is the hula bubble right here. If there's a visual definition for the word undulate, this would be it. One other kind of dance that these bubbles can do, that's the rock and roll. Yeah, will you hold on to that bubble, please? Pretty neat, huh? And of course, there's no wind here, so the bubbles fall very quickly. But you'll find outside, with just a slight breeze, these will go way up into the sky. Here we go. You can do all kinds of things playing around with these bubbles.
For his last trick, Richard did something we'd never seen before. He put two kids inside bubbles.
I can't be sure. Yeah, adults can be in a bubble too, and this is what we call a double bubble. On that note, I'm going to stop.
We wanted to know more about how bubbles work, so we went to see David Katz. He's a chemist who's done some bubble investigations.
David, what recipe do you use?
Well, as a chemist, I've played around with lots of different recipes in the laboratory. The recipe I'm using today uses dishwashing detergent, glycerin, and water. And what I've done is I've measured out 9 scoops of water. And if you'd like to measure out a scoop of dishwashing detergent.
Okay.
And half a scoop of glycerin. Although we can vary the amount of water and use up to twice as much water as I have here right now. Stir that, don't shake, otherwise you have too many suds and it'll take too long for the solution to settle down.
David, you can out of just soap and water. Why do you need to add other ingredients?
Let's take a look at a soap bubble. We have 3 layers. 2 layers of soap, and in the middle is the water.
Soap molecules, water molecules in the middle, and they all cling together.
The water drains out from the soap because it's a lot thinner. The bubble gets too thin up top. It can't support the weight of the rest of the bubble, so the bubble breaks.
So that's why bubbles pop all of a sudden, even without running into anything.
So what we do is we add glycerin, or we add corn syrup, or we can add just a sugar and water solution, and that makes the inner layer thicker, so it flows out much more slowly and the bubble lasts longer. Here's another solution I made. This uses no water at all. It just uses 4 scoops of glycerin, 2 scoops of dishwasher detergent, and 1 scoop of corn syrup. And this makes a very thick, and as you can see, a very goopy solution.
I bet these bubbles last a lot longer, though.
Yeah, the bubbles last a long time with this. You can make this at home, and you can vary the ingredients to see which makes stronger bubbles.
Is this a homemade loop?
Yes, it is. You can make a ring at home just out of a coat hanger. Just like this, using a coat hanger itself. Okay? Or you can stretch it out into another shape. But if you want it to hold more solution, what you can do is wrap some string around it. That will help it make even bigger bubbles. Try it in the bath.
Why is it that no matter what shape you use to blow a bubble, the bubble always comes out round?
Well, the reason for that is the surface tension of the liquid. There's a skin that's formed by the soap molecules on the outside of the bubble. They are attracted to each other, and it tries to pull itself together to form the smallest possible area. And a sphere is the smallest area that could be formed.
Well, why is it that when you get a really big bubble like that, they don't stay round?
Well, that's because the bubble is very, very soft, and when it's very large, it's very easily deformed by air moving around both outside the bubble and inside the bubble.
I still don't understand what you mean by surface tension.
Now, maybe I can show you using some of my wire frames over here. If you'll move that bucket down over here and pick up that prism-shaped frame, dip it in the solution. Now, what happens is the soap tries to coat the outside of the frame, but the molecules are attracted, so it collapses towards the center.
Look closely. The soap film has moved inside the frame. That's because of surface tension. The soap film tries to make the smallest possible surface. This is surface tension, too.
Great. Take your hand off the bottom and watch the string curve towards the center as that film tries to pull itself together.
It's pulling together here.
Mm-hmm. Take that tetrahedral frame, the pyramid and dip that in. In this case, we have 4 different soap films coming together.
On this frame, too, soap that starts out on the outside of the frame comes together in the middle.
If you dip that partway into the solution and take it out, the bubble in the middle wants to be round, but those films on the outside are pushing it out of shape. So it takes the same shape as the frame that it's in.
Does it want to be round because there's air inside?
No, it wants to be round because it's trying to contract to the smallest area.
And make the least amount of surface space.
That's correct.
Can we look at this one, too?
Sure, the cube will do the same thing. All the films on the square try to reach the center, and they actually make a little square section in the middle because there's too many films coming together for it to meet evenly. If you dip that partway into the solution again and take it out, you can see that we form a cubic bubble.
Like if there was a metal bars inside here, that would be this square, this outside square.
It'll still blow a round bubble, though. Mm-hmm. But a free-floating bubble will always try to be round.
I have bubbles in my hair.
Contact. We'll be right back on Noggin.
Possible surface area.
Sure. Let's try some with the wire.
You know, let's make some that aren't regular circles or squares. Okay?
That's a good idea. Do all liquids have surface tension?
Yes, but it's stronger in some liquids than in others.
You're a spiral, you got it. A sphere, you got it. A hexagon's got it too.
If you're a shell, you got it.
A crystal, you got it. A honeycomb's got it too. You got it. You got structure, and structure does something for you. If you're a spiral, you can grow and keep your same shape. Bubbles and beehives, tendrils and turtles, and snowflakes too. All things have structure, feathers and flowers, and so do you. You got it, you got structure, and structure does something for you. If you're a sphere, you've got the most inside for the least amount of outside. If you're hexagonal, you've got 6 walls, and you can pack together tight.
you're a spiral, you got it.
A spin, you got it.
A hexagon's got it too.
If you're a pine cone,
You got it.
a river,
You got it. A
galaxy's got it too. You got it. You got structure, and structure does something for you. Structure does something for you.
Whoops. Check it out. You always get a round form.
Even when it's a square.
Yeah.
Hey, try this one, Stephanie. There are 2 pins between these 2 pieces of plastic. Let's see what happens when we dip it in the bubble fluid. There we go.
It makes kind of a ribbon of soap.
Right. Now, what do you think will happen if we use 3 pins?
I think it'll make a triangle. I know that's the smallest possible surface.
Triangle.
Won't it make a V, though? I mean, that would take up less surface area than a triangle.
Well, let's try it and find out.
Can I try?
Okay. Oh, wait, turn it this way.
Okay.
Ah.
Whoa!
Surprise.
What do you think?
That's the smallest possible surface. This stuff is full of surprises. It's neat.
Here's a way to make a bubble you can keep. You blow a bubble made of glass. Lisa tried it with glass artist Joe Upham.
Joe, it's not as easy as it looks. I was killing myself, and that's all I got.
Well, you're doing fine. It's just that the glass started to cool off and become hard.
Hard. It was falling off before.
Well, now you can see that it's quite hard. In fact, if I hit it hard enough, it breaks. That's one of the properties of glass. When it gets cold, it's very hard. But when it's hot, not only does it look like honey,
Oh, wow.
but it drips,
That's really neat.
just like pouring honey.
Yeah, it does look like honey.
Now you can see this glass, when I hit it with the hammer, nothing happens, because this glass is about 2,000 degrees.
And then when it gets cool, it becomes hard.
That's right. This glass over here has already become very hard and easily broken.
So if I were to take some glass in my house and chop it up like that, would I be able to put it in the oven?
Well, your oven only goes to 500 degrees, so that the glass wouldn't melt.
That's right. What
You
is...
see, the hot glass is like this honey. If you blow through the straw, you can see the bubbles. Just blow very, very gently. You can see that the bubbles form in the honey the same way that bubbles form in hot glass.
What is glass made of, anyhow? I mean, like, I use it every day, but I've never really thought of what goes into it.
Well, the principal ingredient of glass is powdered sand, which is used commercially for making glass. Here's some beach sand. This was used over 4,000 years ago by the Syrians and the Egyptians. But we buy broken glass from a factory that produces glass from these chemicals. And their rejects we throw into the furnace and melt down.
So you get all their mistakes?
That's right. We take this glass and just throw it into the furnace and it remelts. First thing we have to do is make sure that the furnace is up to temperature, 2,200 degrees. Okay, I have a stainless steel tube. It's quite cool at this end, but the end has been heated up red hot.
Yeah.
I'm reaching into the furnace, which is full of molten glass.
That means it's all melted?
Right, the glass is in a liquid state. And you can see how the glass is flowing very slowly back and forth. Okay, now I'm going to roll this on the table. This is the marburing table.
And why are you rolling it?
I'm rolling it to make the outside of the gather symmetrical. Now I'm going to blow through the tube to make a bubble at the end of the pipe.
When you blow a bubble, how come it always comes out round?
It's because there's an equal pressure exerted on all sides of the interior of the bubble. So that forms a sphere when you're blowing.
You couldn't get a square bubble? What if you had a square straw?
No, it would still make a round bubble. Now, this bubble has cooled down considerably, so I have to go back to the furnace and reheat it.
after this?
All we have to do is make a mark on the glass to break this bubble away from the steel pipe. You ready?
Uh-huh.
Okay, now you can see that it's fairly hot now. And if we stop turning it,
Whoa.
the glass starts to fall down and droop. See
What's
how
pulling it down like that?
the force of gravity is pulling against the glass. So if you keep it rolling evenly, the glass will stay symmetrical. Okay, now you just have to squeeze a groove between the bubble and the pipe.
You know, the heat is really coming up from this glass. It's hot. Woo!
Well, it's only about 1,800 degrees now.
Is that all?
Oh, it's cooled off considerably. Now, I'm just using a solid rod this time. And again, I'm reaching into the furnace, gathering some glass on the end of it. I have to go to the marbling table. Yeah, this is going to be the stem on the bottom of the goblet. Okay,
Keep rolling.
keep rolling.
Okay.
Okay, now stop rolling for a second. That's it. That's good. Okay, now roll it again.
Now this just sticks onto each other?
That's right, the glass sticks because it's so hot. Even though this doesn't appear hot anymore, it's still about 1,200 degrees. And you just squeeze this glass with the shears and cut it right off.
It's almost like clay the way it cuts. Just
Okay. I'm just checking the stem now to make sure that it's on center. I'm squeezing with the jacks to make little marks. Now this is going to be the decoration for the stem.
so you can decorate it while it's still hot, huh?
That's right. Now the next thing I'll do is gather some glass on the bottom of this stem. I'll flatten that glass out and squeeze it so it makes a foot, so the goblet has something to stand on.
That just evens it out.
Right. I'll finish squeezing it between the two pieces of wood.
You really make it look so easy. I can't believe it.
It is easy. I'm sure after about 12 lessons you can make something that looks like this. Maybe not exactly like this. Now I'm just taking a small gather of glass. Now I attach this rod to the bottom of the goblet. Let it roll. Make sure it's on the center. Now I just scratch the neck. And tap it. You see that it breaks off from the pipe and leaves a very jagged mark. I just have to heat up the top part of the bubble, and then you can help me open that bubble up so that we can drink out of it. You know, you use those stainless steel tools again, called the jacks, and just put the fingers inside the hole and push up against the top edge of the bubble to open it up.
Spread out.
Just a little bit. That's it, right there. It's good. Very good.
It's really neat.
Okay, there we go.
Is this it? I mean, is it a
That's it.
glass now?
Now here we are, finished goblet.
Wow.
Let's make 3 that join.
Okay. Okay.
Yours is little.
Yeah. Make it bigger. Okay.
Is that 4? That's 4.
No, but this one isn't touching this one.
So there's only 3 touching.
Right, you can always only get 3 touching. Let's see if we can try and get more to touch.
Okay.
Okay?
That's 1, 2.
No, it's
2,
no.
3. See, to get 4, this one over here would have to, oops, we lost one. To be touching the one on the far side.
Well, this one's touching every single one of here.
Which one?
This one, this one, this one.
No, it's only connected to the other ones. It's not touching the other ones.
Oh, that's true.
See? 1, 2.
You know, you always get the same shape though, where they touch.
Right, like when we did the pins.
That Y.
Right. Wait, let's see if we can.
We've got a bubble feast going.
Anybody for bubbles? We learned at the Bubble Festival that the water drains down to the bottom, and that's why they burst. And that's why you see all those colors. That's the water train. Whoa! Yeah!
Bubbles are round, hollow structures that show us a lot about surface tension, the way molecules of a liquid pull themselves together. All liquids have surface tension. They always try to take a shape that has the least possible surface area. You can blow bubbles made of hot liquid glass. A glass bubble goes by the same rules of surface tension as a soap bubble, but instead of popping, it will harden. You can try making your own bubble solution. Experiment with different liquid soaps in different recipes until you get good, strong bubbles. One recipe you can try is 9 scoops water, 1 scoop dishwashing liquid, 1/2 scoop glycerin from a drugstore. Stir the mixture. Don't shake it or get too foamy. Have fun.
321 Contact is a production of the Children's Television Workshop.